Hello everybody, in this lecture we will be solving 1991 IMO problem number 2. Here's a view of this problem. We're given an integer n strictly greater than 6 and a sequence of natural numbers such that each one of them is strictly less than n, and they are all relatively prime to n. Then, if we assume that the common difference between subsequent terms is let's call it d, we easily see that the AIs form an arithmetic progression with, let's assume, A1 the smallest one, and then AK is the largest one. Obviously, because every single one of them is relatively prime to n, and we have the list of all the natural numbers less than n which are relatively prime to n, it's obvious that a1 is 1 and ak is n minus 1. Then it must be the case that n is either a prime number or an integer power of 2, a positive integer power of 2. Okay, I would like to approach it by first considering what happens for different values of d. In particular, I'm interested in this sequence when d is equal to 1. When d is equal to 1, all positive integers less than n, all the numbers less than n apparently are in our progression, meaning that all of them are relatively prime to n, right? So a1 is equal to 1, a2 is equal to 2, and so on. K in this case is equal to n minus 1, obviously. N minus 1. All of them are in the list. They are relatively prime. They're all relatively prime to n. There's only one explanation. It must be the case that n is a prime. And that's pretty good, right? So that explains the first part here. Okay, so for the rest of this problem, let's assume that d is greater than or equal to 2. I claim that a sub 2 is prime, and the proof is simple, and the reason is simple. It's that if it were not a prime, if it wasn't a prime, then it means that there exists, well, it has prime divisors in that case, right? But these prime divisors are definitely strictly greater than 1 and less than a2. When that happens, and knowing also that p is not in our list of relatively prime sequence AIs, right? So it must be that p divides n. So this implies that also p divides n because it's not in the list of AIs. So AIs are all the natural numbers relatively prime to n, right? So for that reason, p must divide n. But then that would be bad because we know that p divides a2. It's one of the factors of a2, right? So, yeah, well, okay, so let's do it here. Assume to the contrary, that a2 is composite and p divides a2, but p is strictly greater than 1. And p is not one of the AIs, right? So it's between a1 and strictly between a1 and a2. It must be the case that p divides n, because if it were relatively prime to n, it must have been in the list a sub i's. But p divides n, p also divides a2, so it violates. This is a contradiction because it contradicts the fact that a2 and n is 1. So therefore, our claim is true, a2 is prime, and also knowing that d is greater than or equal to 2, so therefore not only a2 is prime, but it's also greater than or equal to 3. It's a prime greater than or equal to 3 because a1 is 1, so 1 plus 2 is 3, so it must be at least 3. It's an odd number as well. a2 is odd as well. So a2 is an odd prime. Let's also focus on this thing here. We know that for any, it works for anything, right? So this one, I meant to say this one, yeah. So ak, the largest relatively prime number to n is n minus 1, right? So let's make use of that, I guess, right? So let's go back to the common differences here. So d is obviously even, right? So why? Because d is equal to a2 minus a1, but a2 is an odd number, odd minus, and a1 is just 1, it's also odd. So therefore, okay, so d is even for sure. And as we said earlier, the last term in the sequence, a sub k is equal to n minus 1 as well. So therefore, we can, knowing that a sub I is an arithmetic progression, n minus 1, which is equal to ak, is simply equal to 1 plus k minus 1, because it's the kth term in the arithmetic progression, times d. But then, since d is even, this whole thing is even, and you have the ones which kind of, they are both odd, so therefore n is even. Haha. So this implies that n is equal to 2 times m. But then, now it's we are getting more and more information about our sequence. When you look at our sequence now, our sequence, our arithmetic progression, I should say, our arithmetic progression, I claim that it must be symmetric with respect to n. The terms in this progression is symmetric with respect to m being kind of the middle, the middle, in the middle, exactly, right? But notice that m and n, they are not coprime, right? So this is equal to m, right? Because n is a multiple of m, right? So they are not coprime. As a result, m is not in the list of AIs, right? Because this list contains only numbers and integers coprime to n. So m is not in this list, right? So as a result, m should be in the middle. So you have, if you had to draw the line, the real line, so this is 1, and then we have the number n, and then m minus 1 here. So the AI, so this one is a1, so this is equal to a1, this one is equal to ak, and the midterm, the middle term is, let's call this 0 here. So m is exactly n over 2, right? So this is n over 2, this is m, and this is exactly halfway through from 0 to n, or you can even say halfway through from 1 to n over 2, and then n over 2 to n minus 1. So half of the AIs are on the first part here, and the other half are on the second part here. So therefore, we have an even number of AIs, right? So in fact, what we can do is we can call k is equal to, let me change the color. Okay, k is equal to 2j, right? So we have an even number of AIs. So that's good. And as a result, because they are symmetric with respect to m, the middle, so the one right before m would be a sub j, and the one right after would be a sub j plus 1, and we have m in the middle. The common difference is d. In fact, therefore, we can write the following: a sub j plus 1 minus m is equal to m minus a sub j, and that's simply because the common difference was d, so that this is simply equal to d over 2. Now I make another claim here. I claim that d is in fact strictly less than, has to be strictly less than 6, and a proof, let's assume to the contrary, that d is greater than or equal to 6. In that case, in the interval, so we would have all the following numbers: m minus 2, m minus 1, m plus 1, and m plus 2, all in the interval. So all of these numbers would be in the interval aj plus 1, right? because the common difference, the difference between two consecutive terms is 6, you should have at least 4 terms, and you should have 4 integers at least between two consecutive aj and a sub j plus 1. And all of them, they are not co-prime with n, right? So they share a factor with n, right? So none of these, so let's write that down, none co-prime to n. But so then it means that let p be a common prime factor of n and m minus 1, and in a similar way let p prime be a common prime factor of n and m minus 2. So p must divide, well, it divides n, it divides m minus 1, so it should divide the linear combination of the two. So it divides n minus 2 times m minus 1, but then this is simply equal to 2m is simply equal to n, so this whole thing is 2. So p divides 2, but p is a prime, implying that p is equal to 2. In a similar way, p prime, let's use the second one, divides n minus 2 times m minus 2, but that's simply equal to 4, implying that p prime divides 4, but p prime is prime, so there's only one prime which divides 4, and it's 2. Wow, so this implies p is equal to p prime, but then that's a contradiction, because p is a prime factor of m minus 1, and p prime is a prime factor of m minus 2, and these two numbers are they are relatively prime, right? They are consecutive numbers, they are relatively, there is no way, right, so that 2 would divide two consecutive numbers. So that's the desired contradiction, we found a contradiction. So therefore, so this claim was is sustained, right? So so we have d is strictly less than 6, but we know d is even. I think we found, yeah, so we found it earlier that d was even. So therefore d is either 2 or 4. And let's start with the case, so therefore d is equal to 2 or 4. So let's start with the second case, d is equal to 4. Let's see if this is possible. If d is equal to 4, a1 is equal to 1, a2 is equal to 5, a3 is equal to 9. And here, by the way, the condition that n is greater, strictly greater than 6 is crucial, such that we know a2 equals 5 won't be the last term in this sequence. But then notice that we will have a contradiction, because the prime number which lies between 1 and 5, between a1 and a2, it has to be a divisor of n, right? So 3 divides n, because if it were not, if it was relatively prime to n, it must have been in our sequence of ai's. But then look at the 9, so this is just 3 square. So if 3 is not in this list, 3 square also shouldn't have been in this list, because it is supposed to be co-prime to n, and it can't be, because 3, one of the factors, already divides n, right? So therefore this case can't work. So we are left with only one case, and d is equal to 2. And when that's the case, so what we mean that is that all the odd integers starting at 1 up to n minus 1, they are all this is, you can think of it as our sequence. So this is our sequence. In fact, the last term therefore would be n minus 2 over 2, right? So k is well, okay, so it's possible to figure out what k is, but so all these numbers, for all these numbers being relatively prime to n, there's only one explanation. So all these numbers are relatively prime to n. There's only one explanation, and this implies that n is an integer power of 2, right? So that's the only possibility, right? And that's it. And that solves our problem. Here, if, for example, n had another prime factor, that prime would have appeared in this list, right? So that's why we had only one choice, and it has to be this form. And that solves our problem. Hope to see you in our next video.